Good afternoon and welcome to hand-wavy chemistry. The selective formation of carbon-carbon bonds is such an important part of organic synthesis that almost any time somebody comes up with a new reliable technique to do this, they get a reaction named after themselves. Such is the case with the Wittig reaction. During the Wittig reaction, an aldehyde or ketone reacts with an ylide, which totally sounds like some kind of Lovecraftian monster, and ends up forming not just a carbon-carbon single bond, but a carbon-carbon double bond, which is particularly useful because it means that our product is already functionalized for further reactions. It's also a very easy reaction to predict what the product's going to be without having to spend a lot of time drawing out mechanisms. For example, if we take our carbonyl and our phosphorus ylide and we line them up facing towards each other, and then we take our pair of molecular scissors and we just go snip, snip, snip through the double bonds, switch the oxygen and the carbon over, there is our final product. As simple as that. But clearly this is not the actual mechanism. There are two common ways that the mechanism is usually represented, and in reality they are equivalent. So which one you use tends to come down to how much you can stomach breaking the octet rule versus having extra charges around the place. Let's look at them now. In this first example, we'll use the form of the ylide that has a negative charge on the carbon and a positive charge on the phosphorus. The carbon's lone pair can attack the carbon attached to the oxygen, which in turn will attack the phosphorus, forming a square. And then, following a reverse 2+2 cycloaddition, we get our alkene and our phosphine oxide. Alternatively, we could draw our ylide as a phosphine-carbon double bond, in which case, as that bond breaks and attacks the carbonyl carbon, the carbon-oxygen double bond will break and grab onto the phosphorus. At this point, it's exactly the same. We have a reverse 2+2 cycloaddition, giving us our final alkene. Personally, I like the second reaction mechanism because I can remember it in a very hand-wavy way. Let me show you. I imagine that I am a carbon atom with a double bond to an oxygen, and oh no, here comes an ylide! I'll save you, other carbon! Quick, grab my hands! And just like that, I have formed a carbon-carbon double bond, while ditching the oxygen. Now, obtaining aldehydes and ketones may seem rather trivial. We can buy them at the supermarket. But what about those phosphorus ylides? Where do they come from? Well, they're formed by an SN2 reaction of triphenylphosphine and an alkyl halide. The lone pair on the phosphorus displaces the halogen, forming a phosphonium salt. Treatment of this salt with a strong base generates the ylide. Now that we have an idea of how ylides form and the mechanism of the Wittig reaction, let's do a few practice questions. Okay, so let's take a look at our first question, where we're asked to predict the major product in a Wittig reaction and to justify that prediction by giving the reaction mechanism. We can see that we have an ylide that was probably formed from something like bromocyclopentane is reacting with benzaldehyde. So let's start by bringing the ylide close to our carbonyl group, and then we can have the lone pair on the carbon attack the carbonyl carbon, and the electrons from our carbon-oxygen double bond reaching out and grabbing the phosphorus, giving us that square-shaped intermediate. At this point, we just need to move our electrons around again, and we end up with our alkene and our triphenylphosphine oxide. For our second question, we're once again asked to predict the major product from a Wittig reaction. Looking at our reactants, we see now that we have two aldehydes attached to our benzene ring, reacting with a species that has two ylides in it. We haven't been asked to give a reaction mechanism this time, so I'm going to jump ahead to just after our square intermediate has been formed. At this point, it's that reverse 2 plus 2 cycloaddition we've seen multiple times throughout this video, giving triphenylphosphine oxide and an alkene. At this point, you can see that we still have an aldehyde and a ylide available to react. By following exactly the same reaction that gave us our first alkene, we end up closing the ring, and our final product has two new carbon-carbon double bonds formed. And we have two equivalents of the triphenylphosphine oxide. Now, you may be wondering, why did it close the ring rather than reacting with another molecule and making like a polymer or a long chain? Well, that is because, generally speaking, intramolecular reactions occur faster than intermolecular reactions. And there's also an entropic argument related to having lots of small molecules versus one large polymer. Now, something you may have realized while looking at these practice questions is that since we're forming carbon-carbon double bonds, there is the possibility for different isomers to come about, either an E or a Z form. And you're absolutely right. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.